what we'll discuss is the microstrip antenna, which comes under the category of planar antenna. We have you have seen up to now two types of antennas. One is a half-wave dipole antenna that we were discussing. That is a one-dimensional antenna. It extends along one direction. Other direction, the extension is negligible. Then you saw this antenna, the horn antenna, which has extension in all the three directions. So that is a three-dimensional antenna. Finally, we'll come to a planar antenna, or which is a two-directional antenna. The first antenna in this category is the microstrip antenna. Therefore, we call this microstrip antenna to be mother of all planar antennas. We will be discussing about the microstrip antenna today's class. Now, let me show you what is a microstrip antenna. How does a microstrip antenna looks? We have discussed, when we discussed about microwave theory and techniques, there we discussed about microstrip line. In a microstrip line, we have a ground plane. Then above the ground plane, we have a substrate, dielectric substrate. And then above the dielectric substrate, we have another conducting line or conducting patch. That we can also say as a dielectric substrate, which is sandwiched between a ground plane and a conducting patch. Now, instead of taking a conducting line at the top, if we take a section of the conducting line and such that the length of the section is lambda by 2, or half the wavelength at which we want to design the antenna or we want to operate the antenna, then that forms a microstrip antenna. The structure microstrip antenna, it basically approximates a resonant cavity with short circuit at the top and at the bottom, and open circuit at all the four edges. Let us see a microstrip antenna. This is the bottom side of the microstrip antenna. So you can see a golden plate, and then there is a blue line. So this golden plate is the ground plane. This is a conductor. I will assume it to be a perfect conductor, but it is a conductor. It should be a good conductor. Usually it is copper. So that is what is the golden plate indicates. It is the ground plane, conducting plane. Above that, this blue portion, that is the dielectric. Now, so this is the bottom view of the microstrip antenna. If you look from the bottom, this looks like, the antenna looks like this. Now, if you look from the top, then in the top, and there is a patch. Again, we have a golden plate type of thing, which shows you the patch. The patch is sitting over the dielectric, which is the blue color or copper sulfate color, that is the dielectric. Above that, the patch is sitting. So this is the top view. So between the ground plane and the top conducting patch, they are sandwiching the dielectric, which is the blue color. So if you look at this closely, then at the top and at the bottom we have conductor, and at the four edges there are no conductor. So they are open edges, which means we can say they are open circuited walls. The four edges are open circuited walls. Top and bottom are short circuited walls. Or top and bottom are electric walls, and all the four edges are magnetic walls. So this forms a cavity. I think the cavity is um, enclosed by 6 walls. The top and bottom walls are electric walls. The 4 edges are magnetic walls. So since it is a cavity, it behaves like a resonant cavity, or resonance occurs at discrete frequencies in this cavity. Because a cavity can support only certain modes. How do you form a cavity? I think you remember the waveguide that is shown in the top right hand. In the waveguide, a section of the waveguide, if you take a section of the waveguide, then at the 2 edges, left side and right side, we have open, and all other 4 edges are closed, which means the left side and right side are magnetic walls. All other 4 edges are electric walls or conductors. So in the that forms a cavity, waveguide cavity, and as you know, the waveguide supports discrete modes. The dominant mode is TE10 mode, and if you compare the waveguide with the microstrip antenna, the difference is the microstrip antenna is the dual of the waveguide, or waveguide, section of waveguide and microstrip antenna are dual of each other. Dual means where you have electric wall, whereas you have electric wall in the waveguide, those portions you have magnetic wall in the microstrip antenna. Where you had a magnetic wall in the waveguide, there you have electric wall in the magnetic antenna, microstrip antenna. So that is what it forms. Since it is dual of the waveguide, therefore the dominant mode in the waveguide, the dominant mode is TE10 mode. So the dominant mode in the microstrip antenna will be TM10 mode, because it is the dual of the waveguide. Now, when we excite this antenna at its resonant frequency, what will happen is a strong field will be set inside the cavity, and a strong current on the bottom surface of the patch will be excited. This current will produce significant radiation that gives a good antenna. Now, let us try to understand why it will radiate. That we'll discuss later in detail, but for the time being, the antenna, this microstrip antenna, resembles something like a capacitor. You have 2 plates, 2 conductors separated by a dielectric. So between 2 conductors you have a dielectric. So 2 flat plates separated by a dielectric gives you a capacitor. So it is something like a capacitor. Now if you look at a capacitor, C is equal to epsilon A by D. So if you have more epsilon, epsilon is more, or epsilon is equal to epsilon 0 into epsilon R. Therefore, if you have relative dielectric constant, high dielectric constant, or high relative dielectric constant, then capacitance will be more. Or if you have this separation between the 2 plates, or the thickness of the dielectric is small, D is small, the separation between the 2 plates or the dielectric thickness is small, then 1 by D. So D small means capacitance will be large. So it will have a large capacitance if either D is small or epsilon is large. In both the cases, it will have large capacitances. Since it will have large capacitances, the more the capacitance, job is to store energy. Therefore, it will store electrical energy instead of radiating it. So when we design the antenna, our purpose is to ensure that the capacitance is as low as possible, so that energy stored will be minimum, energy radiated will be maximum. So maximizing the radiation will be done by minimizing the capacitance. Therefore, we should have as small as possible epsilon r. So by taking a small epsilon r, we can have a small capacitance, so good radiation, or having a large separation or large D, or sometimes we call it H. So large H, we can have the capacitance which is small, so therefore it will radiate. Why it will radiate if it has small capacitance? Now you can see these two plates are there. So from one plate the electric lines will extend from one plate, start from one of the plates, end on the other plate. Now if the capacitance is high or dielectric constant is high, or the separation is small, then these electric lines of forces will be tightly coupled between the two plates. If the separation is large or dielectric constant is small, then the lines of forces will be loosely coupled between the two plates. Therefore, it will be easy to radiate, or it will be easy to get detached from the two plates, and you will get electromagnetic radiation from the antenna. So this is the basic principle of radiation of the from the microstrip antenna. Now uh, let us see the basic structure that I described. We have a ground plane. Above the ground plane, we have a dielectric substrate. Above the dielectric substrate, we have a patch. This is the side view. We have seen now the top view, the bottom view, the top view. Now it is the side view. And the patch is fed using a feed line. Now when this occurs, as I told you, the electric fields will be distributed between the patch to ground plane. So electric fields will start from the patch, end on the ground plane, or start from the ground plane, end on the patch. So the field distribution will be something like this that you saw here. The substrate is along the z-axis, so thickness is along the z-axis. Then we have along x-axis the antenna extends, along y-axis is the antenna width. So the patch width is along the x-axis, y-axis, patch length is along the x-axis. Assume that patch length is L, thickness is H, substrate thickness is H. Then you can see the electric fields. So half of the side is from the top to bottom, other half is from the bottom to top. So electric field lines goes from bottom to top and top to bottom. You can see at the edges of the patch, the fields are bent. There is bending in the electric field. I'll tell you why there is bending later, and what is the effect of the bending, that will tell you later. That is called fringing. The electric field fringes out at the edge of the antenna or edge of the top patch. Let me tell you the reason. Simple reason is, as you come to the edge, then electric field will not die down there exactly. For example, if you take 2 points, 2-point charges, the electric lines of forces between the 2-point charges is from one charge to the other in all possible paths. So it is not directly in a straight line, it also goes in the curved lines. So it is something like that happens here. As you come to the edge, the charges on the edge will be there. So from the positive charge, it will come to the negative charge. But when it comes to the negative charge, it will not always be in the straight line. So the curved lines will be responsible for the fringing field. So it will be fringing out of the edge. So from the edge, it will extend outward, slightly extend outward. That we'll discuss on later in details. Now let us do an analysis of the microstrip antenna. Once we are equipped with this knowledge that we discussed up to now, we can do the analysis of the microstrip antenna. Within the microstrip antenna, except at its boundary, exactly on the within the microstrip antenna or within the cavity, it will always support the electric field will be always satisfying the Helmholtz equation. The Helmholtz equation is the dou square Ez by dou x square plus dou square Ez by dou y square plus kmn square Ez is equal to 0. Now why is this? Why Ez? Why not Ex, Ey, etc.? That you know from the waveguide theory, that once you know what is Ez, you can find out Ex, Ey, etc., etc. And in the TM dominant mode, TE mode, in the waveguide, the main field is the Ez field. The longitudinal field that is supported is the Ez field. Here it is dual of that, therefore it will be the Ez field. Main field will be the Ez field. So that is why you will take this. Then k square mn. Why it is k square mn? Why not k square? Because as I told you, it is dual of waveguide. Waveguide supports discrete modes. So this will also support discrete modes. Discrete modes means discrete frequencies. Discrete frequency means discrete propagation constants. Since attenuation constant will be almost 0, we'll assume that there is no attenuation. So attenuation constant will be almost 0. Therefore, there will be distinct phase constant. Distinct phase constant will give rise to distinct wave numbers. Wave numbers are k. These will be distinct, so there will be discrete wave numbers. Therefore, k, mn, m and n represent the mode numbers, the modes. Those are represented by the antenna. Therefore, this will be k square mn. So inside the cavity, this Helmholtz equation will be satisfied. The length of the cavity is L. The width of the cavity is W. So that is what will be satisfied. Now, at the boundary of the cavity, the boundary condition will be satisfied, and as you know, the boundary condition will be the magnetic boundary condition. Since it will satisfy the magnetic boundary condition, along the x-axis, it will be dou Ez by dou y is equal to 0. So along the x-axis, you can see the top and bottom. There we show dou Ez by dou y is equal to 0. Similarly, along the y-axis, dou Ez by dou x will be equal to 0. So on the left and on the right boundaries, there you can see on the boundaries, dou Ez by dou x is equal to 0. So these are the boundary conditions. So these are the two conditions that will be satisfied. What are the two conditions? The fields within the patch are described by a 2D wave equation or Helmholtz equation, and on the boundary, the magnetic boundary wall condition is satisfied. Now, if I take this and solve this, then the solution will be associated with an eigenfunction. The eigenfunction will be given by phi mn. Eigenfunctions will be discrete in nature for the solution of this. So the eigenfunction will be phi mn. Phi mn will be a function of x and y, because Ez is a function of x and y. So phi mn, the eigenfunction associated with Ez will be a function of x and y. So phi mn xy will be of the form amn cosine of m pi x by L into cosine of n pi y by W. From where I got this equation? You remember the waveguide. In the waveguide for TE mode, the solution was of this form: E0 cos m pi x by L cos n pi y by W. So here it will be dual of that. Therefore, it is amn. Amn is the amplitude associated with the mth mode. Then cos n pi x by L cos n pi y by W. This follows the same principle of waveguide analysis. So using this analysis, the waveguide analysis, we get this. We are not going to derive this. Since it is dual of waveguide, we can write this straight away. We can write this. So we write this solution directly. Now, if you look at those solutions, then what is the field distribution? You can see the field distribution here for different modes. The red lines shows the current variation along the length of the patch, and the arrows of those, they show you the voltage variation of the dotted line with arrows. They show you the voltage variation. The top one shows us a TM01 mode or the dominant mode. So if you look at the dominant mode, at both the edges, L is equal to X is equal to 0 and X is equal to L, you will have maximum current because of the open circuit, the maximum voltage because of the open circuit. At the center, you will have 0 voltage, so that you can see the dotted line is maximum at both the edges and 0 at the center. Similarly, current will be 0 because of the open circuit at both the edges, and current will be maximum at the center. So red line shows you the maximum current. Similarly, for TM02, you will have two variations. Here is you have got one half wavelength variation. For TM01 mode, one shows one half wavelength variation, 0 shows no variation along the y direction. Similarly, TM02, it shows two half wavelength variations that you can see. TM03 shows three half wavelength variations that also you can see. So how we saw the current maxima, voltage, where current maxima occurs, there voltage minima occurs. Where voltage maxima occurs, there current minima occurs inside the patch cavity. This is the distribution of current and voltage within the patch cavity. Now let us find out the resonant frequency of the patch. As I told you, it satisfies the Helmholtz equation. Since it satisfies the Helmholtz equation, therefore del square Eg plus k square Eg is equal to 0. This is the Helmholtz equation within the patch cavity for the antenna, microstrip antenna. Now, using separation of variables, because Eg will be a function of x and y, using separation of variable and assuming the amplitude to be 1 or normalizing the amplitude of Ez to 1, we can find Ez is of the form cosine m pi x by L into cosine n pi y by W. This is for the TM-MN mode. Now, once we know that, then let us put this value Ez in the above equation, the first equation, or the Helmholtz equation. If you put Ez is equal to cos n pi by x into cos n pi by n pi y by W, that if you put in del square Ez plus k square Ez, del square Ez now becomes minus m pi by L square minus n pi by W square into Ez. So that is del square Ez. K square Ez remains as it is. K square Ez. So from that you can take minus n pi by L square minus n pi by W square plus k square. Whole thing operating on Ez is equal to 0. Ez is not equal to 0. Therefore, m pi by minus m pi by L square minus n pi by W square plus k square will be equal to 0. That gives us k square is equal to n pi by L square plus n pi by W square. So then now for k we can use k is equal to omega root over of mu 0 epsilon 0 into mu r epsilon r. For most of the dielectrics, mu r is equal to 1. Therefore, we can write k is equal to omega root over of mu 0 epsilon 0 into root over of epsilon r, and where omega, as you know, is equal to 2 pi times f. Then you know c, the speed of light in free space, is equal to 1 by root over of mu 0 epsilon 0. Use all these things for k square. So using this, we will get f is equal to c by 2 pi root over of epsilon r into square root of m pi by L square plus n pi by W square. So this is the expression for the resonant frequency of a microstrip antenna in the mth mode. So for given m and n, we can find out the expression. As I told you, the dominant mode is 1-0 mode. So m is equal to 1, n is equal to 0. If I put m is equal to 1, n is equal to 0, then f is equal to c by 2 pi root over of epsilon r into pi by L. So pi will cancel out, so that will give us F is equal to C by 2 L root over of epsilon r. So that's the expression for the resonant frequency of the microstrip antenna in the dominant mode. Now let us come to the fringing fields. As I told you about fringing fields earlier, so let us come to the fringing fields. We have discussed about aperture antennas. When you discussed about the horn antenna earlier, there you have seen that the radiation comes from an aperture. In the microstrip antenna, similar thing happens here. The microstrip antenna is also a type of aperture antenna. You look at this figure here. If you look at this figure shows you the electric field distribution within the microstrip antenna. Now the patch is the center square patch or center rectangle shows you the patch. Outer rectangle is the substrate. Outer rectangle is the substrate. You can see that as the patch is excited, the field is not confined within the patch. It extends beyond the patch. That is shown here. So at the edge, as you come to the edge, you can see that the field is extending beyond the patch. This is from the simulation that you can see here. Now, since it is extending beyond the patch, the reason I have told you already, I have told you the reason. You can see that the fields are outside, the fields exist outside the patch also, not only within the patch, between the patch and the ground plane, it also exists outside the patch. The fields that are outside the patch are called the fringing fields, and the effect due to which it occurs is called the fringing field effect. The fringing electric fields, they form the two edges of the patch, and they are to the cause of radiation. Reason is, as you go to the edge, so there is nothing which will hold the field. And within the patch, the field will be held between the two conductors. But as you come to the edge, there will be electric field, but there is nothing, no conductor to hold the field. So the field becomes free to move. So the field can radiate out at the edge. As it fringes out, it can radiate out. Therefore, the fringing fields are responsible for the cause of radiation, and they are the radiation. Now, if you look at it carefully, you can see that the fringing fields fringe out not up to infinity but up to a certain small length. That length we'll find out an expression later, but approximately you can take it as h. The length of the fringing field or the edge is extending by an amount of h. H is the thickness of the antenna. So the edge is extending by an amount of h. So the field is distributed along the edge over an aperture. You can say that it extends over an aperture. The thickness of the aperture is h, and length of the aperture is the width of the antenna. So there is an aperture whose width is w and whose the length is w and its width is h. So at both the edges there are apertures. These two apertures will be there. So at one edge there is one aperture. At the other edge there will be one aperture, which means we are separating two apertures at two edges. So two apertures are at a distance of L, separated by a distance of L, and each aperture is like an aperture antenna. So each aperture is radiating. So we have two apertures separated, or two antennas which are separated by a distance of L. If you have two antennas separated by some distance, that forms a two-element array. So ultimately it will form an array, array of two apertures. Okay, next. This you can see the field distribution or field, how it is radiating, that you can see in this animation. The extension of field beyond the edges is shown in this animation. Okay, next. Now since it is extending beyond the edge, so we cannot say that the length of the patch is exactly L. The physical length of the patch is L, but electrical length is not L. It will be something more than L. And we have seen from the expression for resonant frequency, there are two things which control the resonant frequency. One is its length, other is its dielectric constant, because F is equal to, as you know, if in the dominant mode, dominant 10 mode, F10 is equal to C by root over of epsilon R into 1 by 2L. C is a constant, therefore epsilon R and L, they control the resonant frequency. So this is equivalent to saying that the length L is 1/2 of a wavelength in the dielectric. That is what it is, because F is equal to, as you know, F is equal to C by lambda, and C by lambda G, and the lambda G will be here. You are saying 2L root over of epsilon R, that is what is lambda G. Therefore, L is equal to lambda G by 2. So from that you can say this is equivalent to 1/2 of wavelength in the dielectric constant. Now, as you know, KL is equal to pi. That we know. So from that we can say L is equal to lambda G or lambda D. And lambda G stands for guided wavelength, D stands for dielectric. So lambda within the dielectric. So L is equal to lambda D by 2. That is equal to lambda 0 by 2 divided by its root over of epsilon R. Because lambda D is equal to lambda 0 by root over of epsilon R. So that shows that if you have a higher substrate permittivity, which means if epsilon R is high, this will allow for smaller antenna miniaturization is possible if you have a large epsilon R. But as I have told you already, large epsilon R or large dielectric constant will result in large capacitance, so less radiation. So therefore we will have a lower bandwidth. It will radiate exactly at this frequency, but as you move away from the frequency, it will not radiate. So it will have a lower bandwidth. The larger, smaller antenna but lower bandwidth if you have large epsilon R in the microstrip antenna. That is a possibility. Now we have discussed about this extension of the length because of fringing field. Let us say on both the sides, the length extends by an amount of delta L, which will be approximately equal to H expression. Exact expression we will see later. So if we take that into account, then the calculation for resonant frequency will be improved by including the fringing length extension delta L and to each edge. So on each edge it is extending by delta L. So total length will be now effective length LE is the effective length. E stands for effective. So LE is the effective length. That will be L, which is the physical length, plus 2 times delta L, because delta L on each edge. So therefore 2 times delta L. So LE is equal to L plus 2 times delta L. That is the effective length. So instead of using L in the expression for resonant frequency, we can use LE. Now what is delta L? Delta L, the expression for delta L can be found out using this formula. Delta L by H is equal to 0.412 whole into epsilon R effective plus 0.3 into W by H plus 0.264 divided by epsilon R effective minus 0.258 into W by H plus 0.8. This is the expression for W by delta L by H. Since we will know what is H, we can always find out what is delta L. So using that, the F10 expression will be C by 2 root over of epsilon R into 1 by L effective. For most of the calculation, a good thumb rule is delta L is equal to H by 2 or 0.5 H. And epsilon R effective is effective dielectric constant that we have already discussed earlier. Effective dielectric constant is equal to epsilon R plus 1 by 2 plus epsilon R minus 1 by 2 into 1 by root over of 10 H by W plus 1. So that we know already, so I am not repeating that here. Now, to analyze the antenna, we require a model. We use the transmission line model, which is in our course. The antenna, we can assume that there are two apertures at two edges. So the two apertures are connected by the patch. So patch is a conductor. The patch connects the two apertures. So we have two apertures separated by a patch. Patch is a connector and the patch is a microstrip line. We are using a microstrip structure. So it is a microstrip line. Microstrip line is a form of transmission line. So we have a transmission line and of length L, and at the edges of the transmission line we have two apertures. Now each aperture will have some admittance. The admittance will be G plus JB. That will be the form of admittance that you know. So at the two edges of the microstrip line, you can see that we have a microstrip line here. Its length is L. At the two edges are two admittances connected to this. The admittance comes from the aperture. On the first side, it is the conductance is G1, susceptance is B1. So it is G1 plus JB1. Similarly, on the second side, conductance is G2, susceptance is B2. Usually B1 and B2 are same, G1 and G2 are same. Then characteristics impedance of the microstrip line is YC, characteristics admittance is YC, characteristics impedance is ZC. Then we can find out what is the input impedance at any point bit on the transmission line. That will be Yin is equal to Y0 whole into YL plus JY0 tan KL divided by Y0 plus JYL tan KL. This comes from the transmission line theory. So this is for the expression for input admittance. Once we know what is the input admittance, then we can find out what is the input impedance. As you know, impedance and admittance are inversely related to each other. So Zin will be 1 by Yin. So from that we can find out what is input impedance. Now, as I told you, Y1 is equal to G1 plus JB1. Similarly, Y2 is equal to G2 plus JB2. And G1 here is equal to W by 120 lambda 0 into 1 minus 1 by 24 K0 H square when H by lambda 0 is less than 1 by 10. This is an empirical formula. There is no derivation for this empirical formula. So we will use this empirical formula. This formula is given for an aperture. If you look at the book by Harrington, Roger Harrington, in the Roger Harrington book, this formula is given. So from that formula, we have taken this formula. Similarly, B1 is equal to W by 120 lambda 0 into 1 minus 0.636 log natural K0H. Again, H by lambda 0 is less than 1 by 10. And usually Y2 is equal to Y1, G2 is equal to G1, B2 is equal to B1. So this is the transmission line formula for calculation of input admittance and input impedance of the transmission line. We have seen the resonant frequency of the microstrip antenna. We have seen what is the input impedance or input admittance of the microstrip antenna up to this point. This is what is in your course. Mostly this is what will be asked in the examination. So beyond this, let us look at what happens at resonance. Transmission line equivalent at resonance. At resonance, Y2 will be equal to G2 plus JB2, that will be G1 minus JB1. So Y in will be Y1 plus Y2 tilde, that will be 2G1. Now what is this tilde? Tilde represents that we are transforming this point, this admittance to the point where we are going to calculate the input impedance. So therefore, Zin is equal to Rin, because at the resonance, this part, the imaginary part will cancel out, because minus JB1 plus JB1, that will cancel out, leaving out 2G1. So therefore, Yin is equal to 2G1. Once you know what is Yin, then Zin is equal to 1 by Yin, and that will be only Rin, because there is no imaginary part. So Zin is equal to Rin, that is 1 by Yin, that will be equal to 1 by 2G1. We already have seen what is the effect of, or what is the G1, my expression for G1 already. Now there are two slots. Since we have seen two slots, there can be mutual coupling between the two slots. If there is mutual coupling between the two slots, then Rin will be equal to 1 by 2, G1 will be there, then plus minus G12. Or G12 is the mutual coupling between the slot 1 and 2. So G12 will be equal to 1 by V0 square, then real part of surface integration of E1 cross H2 star dot ds, that is what is G12. Now here E1 is the field radiated by slot 1, H1 is the field radiated, H2 is this field radiated, H field radiated by slot 2, V0 is the voltage across the slot. So from that you will find out what is G12. The expression for that is like this. G12 is equal to 1 by 125 square integration from 0 to pi sin K0 W by 2 cos theta y cos theta whole square into Bessel's function. J0 is the Bessel's function of 0th order Bessel's function J0 into J0 of K0 L sin theta, that into sin square theta d theta. This is a take-home problem, neglecting the mutual coupling effect. Find the input impedance of a rectangular microstrip antenna with to height ratio, or W by H is equal to 6 and W is equal to lambda 0 by 2. This is a problem for you, on that you can calculate out. So this is all about microstrip antenna that you require to know. From this, we will move forward onto some practical aspects of microstrip antenna, particularly the electric field. As you know, this is a microstrip antenna that I am showing. L is the length of the microstrip antenna, or W is the width of the microstrip antenna. L extends along x-axis, W extends along y-axis, and there are fringing fields at both the edges of L. So on the left side, the fringing field is from the bottom to up. On the right hand side, it will be opposite. So up to bottom you can take. On the left side from top to bottom, and on the right side from bottom to top, that also you can take. There is no problem in this. Now if it is coming from bottom to top and top to bottom, where there is a curve, when it moves from top to bottom and when it is fringes, So when there is the curve in the field, so that field line it can resolve into two parts. One is along the x-axis and one is along the y-axis. So along the x-axis one will be there, along y-axis will be there. On the left hand side along the y-axis is from bottom to top. Along the x-axis it is from left to right. On the right hand side, along the x-axis it is again from left to right, but on the y-axis it is from top to bottom. So these two, bottom to top and top to bottom, those four components will cancel out in the far field. So in the far field, the addition will be from left to right. That will contribute to the radiation. Others will not contribute to the radiation. So we have a slot here on the left hand side. We have a second slot on the right hand side. The field extends from left to right on both the slots. So the field is uniform, and the slot length is W, slot width is delta L. This is what we have seen. Since there is a slot, the slot supports an equivalent magnetic current density Ms. So each slot will support an equivalent current density Ms. Within the patch, the electric field will be of the form EMN, that will be the form E0 into cos m pi L by capital L, cos n pi W, small w by capital W, capital L and small capital W are the length and width of the patch. So this will be the form. Then E10 in the 10 or dominant mode, it will be E0 cos pi L by capital L, and on the aperture EA it will be E0, it will be constant fixed. L is equal to 0. Once you put L is equal to 0, it will be constant E0 because cos 0 is equal to 1. So on the aperture, the electric field is constant E0. EA is equal to E0 on the aperture. EA is equal to E0. Now once EA is equal to E0, once you know what is the field on the aperture, then you can find out what is the magnetic current density, equivalent magnetic current density. So that will be Ms, that is equal to 2 EA cross n cap, that is the magnetic current density. Once you know what is ES, then you can find out what is E theta and E phi for each slot. So E theta will be of the form E0 cos phi F theta phi, that is equal to E0 cos theta sin phi F theta phi. E phi is equal to minus E0 cos theta sin phi F theta phi. F on theta phi is the far field due to each of the slots. Now, if I take the array, then that will give me F theta phi is equal to sin kW by 2 sin theta sin phi divided by kW by 2 sin theta sin phi. This is because of the slot. Then because of the array, then you will get cos kW by 2. Sorry, this will be cos kl. Cos kl by 2 sin theta cos phi. So that will be because of the array. So from that we will find out what is F e theta, that will be cos kW by 2 sin theta. Similarly, we can find out what is F h theta, that will be cos theta sin kW by 2 sin theta by kW by 2 sin theta. In the H plane, phi is equal to 90 degree. In the E plane, phi is equal to 0 degree. So from that you can find out what is Fe and Fs. That is what we have found out here. Now let us look at the pattern, because once we know these expressions, we can find out what is the pattern. The E plane pattern is typically broader than the H plane pattern. From this source, that E plane pattern will be broader than H plane pattern. The truncation of the ground plane, because the ground plane is not infinite, it will be finite. So the truncation of the ground plane, that will cause edge diffraction. At the edge of the ground plane, there will be diffraction, which will degrade the pattern because it will introduce rippling towards the forward direction and as well as back radiation. So in forward direction there will be radiation, in backward direction also there will be radiation. because of the finite ground plane. Had the ground plane been infinite, then there will be no ground back radiation because everything will be reflected back. Now, because it is finite, there is no reflection, some back radiation will be there. The vertically polarized E theta and surface wave patterns are angle dependent, both vary as cos phi. So that also gives you to some distortion in the radiation pattern. The distortion is more severe in the E-plane pattern. You can see the E-plane pattern and the H-plane pattern, 2D patterns of the E-plane and H-plane. Here what we have done is, we have taken a practical antenna and an ideal antenna. The red line that you see, this is the ideal antenna. So ideal antenna means we are taking infinite substrate and ground plane. So extension of the ground plane and substrate are infinite. There you can see that there is no rippling, it is very smooth and there is no back radiation. Whereas when you take a ground plane of 1 meter, so 1 meter ground plane, you can see there is rippling and there is back radiation that we discussed. You can see this in 3D also. The 3D patterns are shown here. Back radiations are there, forward radiation are there, rippling are there. So everything is here. Now let us come to the radiation resistance of the microstrip antenna. The resonant resistance or the resonant frequency, what is the resistance that is called the resonant resistance of the microstrip antenna. These are now from this point onward that we will discuss in the next 2-3 minutes. These are about the microstrip antenna practical aspects. If you are designing an antenna, what are the practical aspects? Those things we will discuss and then we will stop. So up to now what we have discussed is from the theoretical aspects or from the examination point of view. Now if you are going to design a microstrip antenna, some small hints about how to design a microstrip antenna that I am going to give you now. Now the resonant resistance, this is almost independent of the substrate thickness. It does not depend on the substrate thickness H. This is always proportional to epsilon r. It is controlled by the location of the field point. It will be maximum at the edge when x is equal to 0, and it will be minimum at the center. So at the edge when x is equal to 0 or x is equal to a, it will be maximum. At the center it will be minimum. Generally what we do is we feed the microstrip antenna along the center line. So when y is equal to w by 2, that maintains the symmetry and minimizes excitation of undesired modes. So TM10 mode only is excited. This is proportional to the square of the cavity field. So Rin, so resonant resistance is proportional to Ez square, and Ez is dependent on x0, y0. X0 and y0 is the radiation, is the feed point. X0 and y0 gives you the feeding point. For 1-0 mode, now we will get Rin is proportional to cos square pi x0 by L, or you can say proportionality constant. If I take Rin is equal to RH cos square pi x0 by L. Now if you put x0 is equal to 0, this will be cos 0. So Rin is equal to RH. So RH, from that you can say that the proportionality constant is equal to RH. RH means the input resonant resistance at the edge. So RH, that depends strongly on the substrate permittivity. Typically it will be about 100 to 200 ohms. Now let us come to the bandwidth. Bandwidth of the antenna. Bandwidth is affected mostly by substrate and geometry. Their effect is more on the bandwidth. Directly proportional to substrate thickness. If H is very high, say for more than 0.05 lambda 0, then the probe inductance becomes large because you are going to feed it using a probe. So the probe inductance will be large. That will make the matching difficult, so antenna feeding will be difficult. Bandwidth is inversely proportional to epsilon r. So smaller epsilon r, larger bandwidth. Usually we take AR substrate, therefore that gives you the smallest epsilon r. Epsilon r is equal to 1 for AR substrate. So very close to air is foam. Usually foam is used. Now, usually what we do is we take W to be less than 2L, and typically W is equal to 1.5 times L when you are designing it. Typical results is about 3% bandwidth for a microstrip antenna. Conventional microstrip antenna gives you 3% bandwidth using typical substrate. H by lambda 0 is equal to 0.02, and typical permittivity is 2.2. This becomes around 10% when thick foam substrate is used. There are special feeding techniques like aperture coupling, stacked patches that we'll see later. They can increase the bandwidth up to 50%. So this is about bandwidth. Figure, forget it. Next. Then directivity. Directivity of the antenna, microstrip antenna, is insensitive to the substrate thickness to a large extent, but directivity is higher for lower permittivity as the patch becomes larger, electrically larger. Efficiency similar to directivity, so don't look at this. Then we'll see the advantages and disadvantages of microstrip antenna. Advantages of microstrip antenna is it has low profile, so size is small. So even it can be conformal to any surface, so conforms to surface. Easy to fabricate. Simply use photolithography technique or PCB technique, etching technique. They can be used to fabricate a microstrip antenna. Easy to feed. You can easily feed it. So energy can be fed easily. Easy to use in an array or incorporate with other microstrip circuit elements on the substrate, like on the PCB. You have cell phones. In the cell phone and the PCB, your microstrip antenna is mounted. If you look at the laptop, on the PCB, the microstrip antenna or antenna is mounted. Then patterns are somewhat hemispherical with a moderate directivity, about 6 to 8 dB directivity is typical. Disadvantage, then it is cheaper compared to other antennas. Disadvantage is bandwidth is low, few percentage, about 3%, but techniques exist to improve the bandwidth. Then efficiency may be lower than other antennas. Efficiency limited because of the conductor and dielectric losses in the microstrip type of structure, severe for thinner substrate. Then there are surface wave losses which also affect the efficiency because some loss or some radiation because of the surface wave. So then we will stop here. Feeding methods, etc. we will not discuss. We will stop here. These things we can discuss later, sometimes else. But here we will stop for today. So thank you. OBS.
Sir.
Just a minute.